Welcome to Lecture 12.1, Gradient-Based Optimization for Introduction to Programming in Mechanical Engineering. By the end of this lecture video, you will have an understanding of the advantages of gradient-based optimization over parametric sweep, how gradient-based optimization actually works, how to implement gradient ascent for a simple unimodal surface, and the limitations of gradient-based optimizations for multimodal functions. This slide, the table of contents, contains hyperlinks to each of the sections to make the downloaded PDF easy to navigate. Last lecture covered optimization by parametric sweep. Recall that the entire method rests upon testing the whole domain for each parameter of your system. This requires either knowing that there is an extremum within some small region, just not the exact coordinates necessarily, or casting a large enough domain to confidently catch the extremum. But, of course, this comes with a tangible computational cost for testing larger domains. This is especially true for multi-parameter problems, which requires sweeping several large domains. Gradient-based optimization addresses this by algorithmically converging towards an extremum in comparably few steps. How does it work? At a very high level, we want to follow the direction of the steepest slope. We already have the perfect tool for this in math, which is the gradient. This denotes the steepest slope of the surface f. We recall the simplest case where the gradient of f of x is just equal to the single derivative df of x dx. Now, to optimize a function, we take consecutive small steps along the gradient to iteratively approach a maximum or a minimum in the surface. If we consider the following surface, f of x and y is equal to negative x squared plus y squared plus 10, gives us this three-dimensional surface. If we start with a random point, denoted here with a red circle, and then take a step following the gradient of f along that direction, we can take a couple more. We see that it is starting to approach the top of this curve, which we know is the maximum. And then if we skip the rest, we can see that ultimately it does in fact converge towards that point right at the top. By following the gradient, the algorithm systematically approaches the global maximum of this function. We reach the exact same result regardless of where we start. Here you can see 4 different starting points, and they all converge towards that same 0, 0 on the xy axis as the maximum. Note as well that the surface here is shown just as a visual aid. The algorithm does not actually compute that surface, unlike with the parametric sweep. Now, what does it mean to take a step along the gradient of f? The input coordinates, x, in this case is a vector, they get updated with each iteration according to the following formula. For gradient ascent, we have x of I is equal to x of I minus 1 plus alpha times the gradient of f of x evaluated at x of I minus 1. And for gradient descent, that plus turns into a minus, meaning that rather than going with the gradient, you go against it, meaning you're minimizing the function. In both of these cases, x of I represents the location of your coordinates in the current iteration, and x of I minus 1 is the coordinates in the previous iteration. After we define a start location in the very beginning of the algorithm, we want to iteratively update the coordinates according to that formula. Note that alpha represents the overall step size parameter. This is tunable, but we will mostly ignore it in this lecture for simplicity. We'll just set it to a constant. Upon updating the vector x, your coordinates, you evaluate the difference between the previous iteration and the current iteration and the norm of that vector. you continue until that norm is less than some convergence threshold. For now, we will use the MATLAB built-in EPS function, which is the numerical precision in MATLAB. We can start with the implementation, defining the function f of x of y. Note that this is not a necessary step, but it is necessary if we want to graph the function surface itself, which for educational purposes might be useful. Then we can define the gradient of f of x and y. Here, this is an anonymous function. In some cases where you don't have the analytic form of your surface, it might be necessary to change this implementation into a numerical approach, following some of our examples in previous classes with the finite difference method. Then we can initialize a couple of parameters. For example, x and y are our starting positions. Delta will represent the norm of the difference in the coordinates, and we'll initialize that to infinity. And then z and pos will initialize to empty arrays because we want to store things in them. And then alpha represents our step size parameter. We'll set that to just 0.1. Now we can set up the while loop itself, and our condition, our threshold, is that delta remains above epsilon. In MATLAB, eps is the floating point relative accuracy. It's a very small number. You can look up the documentation for it. And the first thing to do within that loop is to actually evaluate the gradient, because we use that to then update the values of x and y, the two coordinates. And again, this is following the formula from before. We're using x equals the previous value of x plus alpha times the gradient in x, and y, we do the same thing. Then we can calculate the differences between the old positions and the new calculated positions, and then calculate the norm of that difference vector, delta. And that's what gets compared to eps at the beginning of each loop iteration. Once that converges, we can print out our results using the arrays in order to get the following results. Now notice, this is enough to fully define a gradient descent algorithm. For our example, we see here that starting at 4.5 and negative 4.8 converges to the following output. The optimal point is 0, 0, 10, which, if we recall back to the equation, this should make sense. And it reached it in 164 steps. I will point out now that the number of steps required to reach the solution will vary according to the value of alpha. In this case, we used an arbitrary value of 0.1. If you use a slightly larger value, you might converge faster, and if you use a lower value, you will converge slower. But the value of alpha will depend on the sensitivity of the function, so it's not a one-size-fits-all number. Now, I'm not going to go over this, but this is our plotting function, and we can see the results that we actually have already seen, which is this figure shown here. We see the steps being taken from the starting point all the way up to the top of the surface. Now, the surface from that example is considered to be unimodal because it only has one maximum point. Multimodal functions have more than one extremum. That could be a maximum or a minimum. Such functions might have several local extrema, even if there's only one global extremum, meaning some of them might be less than or greater than the ultimate maximum or minimum, but they are still maxima or minima nonetheless. The simple implementation that we've covered in this lecture cannot reliably find the global extremum for multimodal functions. We'll demonstrate this here with the following surface, which has 4 maxima. We see here, there's one in each quadrant of the surface. Starting at 0 and negative 4.8, we reach the first maximum, which is at negative 3.78 and negative 3.28, and has a value of 0. But if we shift our starting point by just 0.5 in the x direction, we actually converge to the other maximum. And then if we switch sides to the surface, we see that we converge to a third maximum. And again, in this case, if we shift back over, we make it to the fourth maximum point. Now, optimization methods in general constitute a whole field of study unto themselves. The past two lectures have barely even scratched the surface of these things. Optimization is one of those things that is hugely applicable out in industry, especially for data-informed modeling in engineering. You now have an introduction to the subject, and I encourage you to explore it more deeply on your own. It may be useful in future classes or for personal projects. To summarize, this lecture covered first the advantages of gradient-based optimization over parametric sweep, which is that we avoid having to evaluate an entire domain, which is especially great when you're trying to optimize multiple parameters. Then the gradient descent and ascent algorithms work by following the gradient of a surface in small iterative steps. The algorithm actually converges towards an extremum by doing this. And to actually implement this in code, we define a function that evaluates the gradient of a surface, which in our example was an analytic function, but like I said earlier, this could be a numeric implementation. And then inside of a while loop, we iteratively update the coordinates of the test until the change in those coordinates decreases below the numerical threshold. And finally, gradient-based optimization from this lecture fails to obtain the global extremum for surfaces that have multiple local extrema. It might converge differently depending on the starting conditions, and that's something that you should watch out for.